Section 13.2, line integrals, video 13. When setting up for this last video, I realized that the alignment of the video with the board in the previous videos might have been a little bit off. Some of the top of the screen might have been cut off. I'm not 100% sure. If you have trouble seeing anything on the board, please contact Mr. Walker and he can contact me and we'll get it straightened out. But let's take a look at an example of a line integral of a vector field. Now this is sort of example 7 on page 769, except I've made a couple of changes. First, let me read the problem. Find the work done by the vector field f of xy equals x squared vector I minus xy vector j, and moving a particle along the unit quarter circle in quadrant 1, oriented clockwise. So here's the changes I've made. Number 1, in the problem in the book, the orientation is counterclockwise. In other words, the normal direction along a unit circle. And also in the book, they give you the actual position function to describe the path, as opposed to me just giving you a geometric description. So I've made this a little bit more work involved because we have to parameterize our path. So let's start there. Let's start by parameterizing the path. Well, let's first start by drawing it. If we're in the unit circle going clockwise, we're going in that direction. Our point at the top is 0, 1. Our point at the bottom is 1, 0. There is one thing that I casually mentioned before that is worth mentioning now. Everything that we've done in these last few videos has been an R3 in space, an X, Y, and a Z, or in terms of I, J, and K, an I component, a J component, and a K component. All of that can be collapsed down to a problem in 2 dimensions by simply assuming that the K component function is equal to 0. So in all the previous work that we did, we would just say Z of t is equal to 0. It's pretty intuitive, but anything that happens in 2 dimensions can be embedded inside of 3 dimensions. Same thing with 1 dimension being embedded inside of 2 dimensions, and even higher. But anyway, I digress. So here's our path, and we need to parameterize it. Now, in a previous video, we looked at some common parameterizations, and one of them for a circle was saying that xt equals cosine of t and yt equals sine of t. I'm going to take a slightly different approach here. Actually, let's not. Let's go with that. I don't want to throw something out there that suddenly is different out of nowhere. I'd rather give you something that's a little bit more reliable. But if we're going to orient this curve correctly, we need to figure out the lower bound for the t and the upper bound. So when we set up our integral, we know what numbers to put here. So our lower bound is the value of t that would put us up here. So what value of t would make cosine equal to 0, but sine equal to 1? And the answer is pi over 2. I'm going to put quotes around lower because our, quote, upper bound is actually going to be less than pi over 2. So if we're over here at the beginning, then we need to be over here at the end, and what value of t would give us a cosine of 0 and a cosine of 1 and a sine of 0, and the answer is t equals 0. So when we set up our integral, it will be from pi over 2 to 0. Which looks weird, but it's perfectly legitimate. All right, so now we have our position function. Our position function is going to be cosine t of I plus sine t times j. Now we've got everything that we need. Let's now use let's use this version, FDR. So our integral is going to go from pi over 2 to 0. And we need to evaluate this function when x is cosine and y is sine. So we would have, and I'm going to shift notations for a minute. I'm going to go to the pointy parentheses notation. I prefer that when you're doing a dot product because that way you don't have to worry about the i's and the j's. So our our vector field evaluated at our position function, each x becomes cosine t, each y becomes sine t. So the I component becomes cosine squared t, and the j component becomes the negative product. So negative cosine t sine t. And now we have to multiply that times the derivative of the position function. Well, that's pretty easy. Again, shifting notation from ij to the pointy parentheses. The dr is going to be the derivative of the position function, so the derivative of cosine is negative sine, comma, and the derivative of sine is cosine. And that will be dt. Remember, dr is the derivative of r times dt. Okay, now for the dot product. Still going from pi over 2 to 0. For the dot product, it's just the sum of the product of the corresponding components. So we start by multiplying these two, and we would get negative cosine squared t sine t. Pretty easy to integrate with the substitution. And then we add the dot product of the second components. Then we add the product of the second components. The second components are negative cosine t sine t and cosine t. So if I multiply those, I get negative cosine squared t sine t. dt. Hey, these are like terms, hooray. So the integral from pi over 2 to 0 of negative 2 cosine squared t sine t dt. This is screaming substitution. Anytime you have the integral of cosines and sines, one of them is a power and the other one's just one of them. You can always do a substitution of u equals whatever has the power. The other one will be used for the du. So let's just figure out the substitution real quick. U is equal to cosine of t. So du is equal to negative sine of t dt. So let's grab all the things we need for the du package. The dt, the sine, and the negative. So all three of the double underlined parts become part of the du. Let's move this over here. Integral pi over 2 to 0. And because I'm about to change variables, I should probably write t equals just for clarity. I'll tell you, one of the tricks to good math is to make it impossible to be misunderstood. So by writing t equals, there's no way I can accidentally think those are u values. All right, so everything double underlined in green becomes du. Cosine becomes u, but the cosine has a square on it, so it's u squared. Oh, don't forget the 2. I did not need the 2 for the du package, so it's still there. So we have this integral of t equals pi over 2 to t equals 0 of 2u squared du. So the antiderivative of 2u squared is 2/3 u to the third power from t equals pi over 2 to t equals 0. Now it's time to undo the substitution. U is holding the place of cosine. So we have 2/3 cosine to the third power of t from pi over 2 to 0. We don't need the t equals now, it's the correct variable. If we substitute 0, the cosine of 0 is 1. 1 cubed is 1, times 2/3 is 2/3. Minus, if we substitute pi over 2, cosine of pi over 2 is 0. So 2/3 times 0 cubed is 0. And the total work involved to move this particle along that quarter circle is 2/3. So at the end, it's actually pretty straightforward. And there we go. Now, I was just checking with the problem in the book because I told you that I changed the orientation of the path. That the path was going from here, I took it from the top of the quarter circle down to the right side, but in the book it's actually from the right side upwards. In other words, the path goes counterclockwise. What do you think that would do to the answer to the problem? What do you think that would do if the path were oriented the other direction? If in this direction the work was 2/3? Well, let's think about it calculus-wise and see if it makes sense in a physical context. If we were going the other direction, the only thing that would have changed was the order of the bounds. It would have gone from 0 to pi over 2. which means the subtraction problem would have been in the reverse order and given us a value of negative 2/3. So it kind of makes sense that if we move the path in the opposite direction, we have the negative value for the work. I'll be honest, as a pure mathematician, as a theoretical mathematician, as opposed to an applied mathematician, I'm not exactly sure why it makes sense for the work to be done to be negative. I'm sure if I sat down and read about it for about 5 or 10 minutes, I would go, oh, that makes sense. But I digress. And I believe that takes care of it. Just for reference, on page 770, there is another example of a line integral of a vector field in 3 dimensions. I would recommend taking a look at it just to have another example. Oh, I do have one thing to say in closing, but I'll put it in the next video.